So today I'm going to talk about the Doppler's effect here. So what is Doppler's effect? So here Doppler's effect is the change in frequency. For example, let's say a sound source, a speaker or something is emitting a sound of frequency 200 Hertz, and it is traveling towards an observer, a stationary observer, with a velocity, let's say 30 meters per second. Now this observer who's stationary will not hear the same frequency that is emitted by the sound source. For example, he will hear a frequency higher than this amount. So this apparent change is called the Doppler's effect. So let's see how this happens. For example, we'll take the same example. Let's assume in the first case both are at rest. So here the velocity is 0 and the observer is also at rest. Now what will happen is when a sound source is emitted, let's say when a sound wave is emitted of the frequency 200 Hertz or whatever the frequency, it travels like this towards the observer. So the distance between two wavefronts, we can take it as the wavelength. And next, if we take the scenario where the sound source travels towards the stationary observer with a velocity v or something, in the first time when the wavefront is emitted, when the next wavefront is going to emit, let's say in this time, so this source has traveled a distance, let's say a little bit compared to the velocity of sound, but if you observe properly, now the distance between two wavefronts will be minimized because now this is traveling towards the stationary observer in this direction. So what will happen? Now we will get a lesser distance between two wavefronts than in the previous case. So now the lambda or the wavelength will be minimal, smaller than the previous amount. So if we take v equals f lambda, now wavelength being smaller means the frequency will be larger. So this is basically the Doppler's effect. So this effect can happen at any time when there's a relative motion between source and an observer. So let's take how to calculate the frequency heard by the observer. So we take the Doppler's equation is f dash is equal to velocity of sound relative to observer divided by velocity of sound relative to source multiplied by real frequency. So this is the apparent frequency. So here if you observe properly, so you don't have to worry in which direction, actually you don't have to remember four or five equations, you can just remember this equation. So using this equation you can find the frequency heard in any situation. That means whether the sound source is reaching the observer, going away from the observer, or whether both are moving, or whatever the scenario. For example, let's take the same case. Now let's assume this velocity of sound to be 340 meters per second, and now the frequency of sound source to be 200 Hertz. Now let's assume the observer is stationary. That means velocity is equal to 0, ms minus 1. And now let's assume this source speaker is moving towards the observer with a velocity of 30 meters per second. Now let's find the frequency heard by this observer. Now to do that, so f dash means the apparent frequency is equal to velocity of sound relative to observer. So what is observer is at rest with respect to the velocity of sound. So we can take 340 meters per second divided by velocity of sound relative to source. Now sound travels in this direction with a velocity of 340 meters per second, and the source also travels in the same direction with a velocity of 30 meters per second. So the velocity of sound relative to source will be 340 minus 30. 340 minus 30 meters per second multiplied by the real frequency, which is 200 Hertz. So simplifying this one, we will get the frequency heard by the observer. So similarly you can work out for the other instances also, when the source is moving away from the observer, or when both the observer and the source are moving towards each other or away from each other, by finding the respective relative velocities.